Section 17 of the Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by J.E.D. Klein. The Outline of Science, Volume 3 by J. Arthur Thomson. Section 17. 24. Applied Science. 1. The Marvels of Electricity. The Age of Electricity. Our age is the age of electricity, the remarkable revolution which the practical application of electricity has effected in recent years is one of the wonders of modern life. To electrical engineering science, the civilization of today owes more than is readily realized. It has solved many great problems which modern conditions of life called into being, and which had to be solved if further progress was to be looked for. Professor J. A. Fleming, who has given 50 years to studying the problems of electricity, has said that the outlook for electrical engineering has vast possibilities which may materialize at any time and make ancient history of our present achievement, great as that is. The records of the past half-century are wonderful enough. The next 50 years of electricity, it is interesting to learn from such an authority, is a subject for attractive meditation. Space and time have been almost annihilated. The transmission of energy, the development of production, and distribution of electrical power all suggest great possibilities. We have seen in previous sections of this work the interesting stage physicists and chemists have reached in their investigations into the constitution of the atom, and how these investigations had transformed our fundamental conception of matter. The discovery of the electron as a mobile constituent of the atom of matter has, Sir Ernest Rutherford says, exercised a wide influence on electrical theory, and has been the starting point of attack on numerous electrical problems. Long before this discovery, electricity had become our handmaiden. It was a mysterious force, the nature of which was little understood, but we now know a great deal about the old-time mysterious forces of electricity and magnetism. The revolution which has been accomplished in modern life by electricity has been so quietly effected, so steadily cumulative, so all-embracing that the ordinary man, perhaps, fails to appreciate the scope and the majestic proportions of the work of modern electrical engineering science. A cinematograph picture that would contrast things as they were done only 50 years ago with the same things done by means of electricity today would strikingly illustrate the triumph of applied electricity. The Institution of Electrical Engineers celebrated its jubilee in March 1922. Less than 50 years ago, the electrical engineer was looked upon as a glorified showman, displaying his wares from town to town. Sir Alexander Kennedy, at the meeting referred to, recalling the electrification of the Houses of Parliament in 1890, said he remembered an urgent request that an effort should be made to keep the lights steady, especially during the Speaker's dinner. Sir Oliver Lodge described the impetuous course of the first British electric tram, which came to rest in a shop window. Godalming was the first town to be lighted by the swan lamp, and Mr. S. Evershed related how the supply cables were laid in innocence in the open gutter. The present generation has grown up with the ever-evolving wonders of electricity, and has probably ceased to wonder at them. The majority of persons know next to nothing about electricity, and few could explain the principles that underlie the generation, transmission, and utilization of electrical energy. It would be a task even to enumerate the various spheres of the wonder-working activities of electrical power. It will drive the Transcontinental Express up the dizzy heights of the Rocky Mountains. It will haul trains of 800 tons weight over the mountain ranges of the Alps. It will flash its wireless messages across the Atlantic at the speed of 186,000 miles a second. It will supply all the light and heat the greatest city could want. Long submarine electric cables connect the most distant lands, but such cables become more and more dispensable. You can converse with a person in Paris without using wire or cable. You can talk to an air pilot hidden behind the clouds. Some of our greatest industrial undertakings are solely devoted to electrical engineering practice, and in almost every phase of industry it plays a part. In the coal mine we have electric coal cutters, haulages, and winding machinery. In the modern iron foundry, the electric furnace, which will produce temperatures up to 6,000 degrees Fahrenheit. In the engineer shop, the electrical arc for welding all manner of metals and alloys. In factories, steam power and mechanical transmission by shafting and belt is almost displaced by electric motors driving separate machines, or groups of machines. And even for the propelling of ships, electrical energy transformed from the mechanical energy of the steam turbine has been applied successfully. We cook by electricity, do our laundry work by electricity, sweep our homes by electricity. Even the dentist's tiny drill is whirled round by electricity. We have electromagnets powerful enough to lift 10 tons of scrap iron. The medical man may use a magnet to extract fragments of steel from a workman's eye. Ease of transmission. The cause of the enormous vogue of electrical power is to be found in the fact that energy can be transmitted and distributed in its electrical form very cheaply and efficiently. Where distances are considerable, electricity has the field to itself. If a large amount of energy has to be transmitted to a point, say 100 miles away, the alternatives are air under pressure, water under pressure, and electricity. For the first would be required huge pipes, expensive to make, lay, and maintain, and, in spite of the greatest care, these pipes would be sure to leak and a large amount of power would be dissipated. Hydraulic transmission would also need very large pipes, very deep to escape frost. For carrying the energy as electricity, small insulated conductors buried in the ground, or carried aloft on poles, suffice. The conductors may change direction suddenly, twisting and bending about to suit natural conditions, without the loss of efficiency, which inevitably would result in the case of pipes carrying fluids. Rivers, wide chasms, and other natural obstructions present difficulties not comparable with those encountered by a pipeline, as the conductors negotiate them in huge spans. Cheap and efficient transmission, then, makes it possible to generate current in bulk at centers where conditions are favorable for generation, and deliver it over large areas at a lower price than it would cost if generated in small quantities on the spot. The energy converted may be either that of fuel capable of transport, such as coal or oil, or, again, that of waste gases or falling water, which can be converted profitably only where available. As for coal, under certain conditions it may be more economical to move it to where energy is wanted than to transport current. But it cannot be denied that judiciously distributed central power stations produce a given amount of power much more cheaply than a multitude of independent plants. For railway working, 2 pounds of coal consumed in an electric power station will do the work of 5 to 7 pounds burned in a locomotive. On the other hand, the energy in the waste gases from a blast furnace or a natural heat must be converted on the spot or not at all. Hence many smelting points become centers from which electric power is distributed in all directions, as much as 4,000 horsepower being obtainable from one furnace, and places where terrestrial heat is available in sufficient quantities acquire new importance. Thus at Lardarello, in a volcanic district near Volterra, Italy, subterranean steam is brought to the surface in pipes and made to generate 10,000 electrical horsepower for transmission to Leghorn, Florence, and Pisa, to which points the steam itself obviously could not be piped. What a current of electricity is. What we know today of the nature and interrelationship of electricity and magnetism has been explained in a previous chapter. The electromagnet, in some form or another, is the basis of all machines for generating electric currents by mechanical power called dynamos, of electric motors, induction coils, and other applications. The electromagnet is at the bottom also of all modern electric telegraphy and telephony. It was the crowning discovery of Michael Faraday that a current of electricity could be induced in a closed coil or ring of wire by moving it towards or away from a magnet. In other words, by moving it across a magnetic field. Faraday was also responsible for the first dynamo. What is a magnetic field? An electric current is the flow of electrons passing from atom to atom. If we put zinc and copper together, we get a mild current of electricity. The atoms of zinc are particularly disposed to part with their electrons, and these electrons pass to the atoms of copper. Their passage is a current. An atom is giving up an electron to its neighboring atom. If the metals copper and zinc are immersed in certain chemicals, which slowly dissolve the zinc, and the two metals are connected by a copper wire, the current is stronger. There is a brisker flow of electrons. Copper, in other words, is a good conductor. Now we have also seen that there is no movement of electrons without their creating an attendant field of energy. A magnetic force due to the electric current exists in circles around the wire, and results in an ether disturbance or strain. Thus the space around the path of an electric current is filled with lines of magnetic force, and we have what is called a magnetic field. Faraday therefore found the means of creating an electric current by causing a coil of insulated copper wire to spin round the ends or poles of a horseshoe-shaped magnet. He gave us the first Magneto electric machine, developed now to such a wonderful extent. Every taxicab, motor bus, or motor vehicle contains a Faraday magneto, used to make the electric spark which fires the charge of petrol vapor and air in the cylinder. Every gigantic dynamo in electric lighting or power stations is only a descendant of that first rudimentary magneto machine which Faraday made by spinning a circular copper plate between the poles of a powerful magnet in the laboratories of the Royal Institution. The simplest illustration of how an electric current is induced in a wire is to take an ordinary horseshoe-shaped magnet, which everyone has seen, and with the horns kept upright, move a section of a copper wire ring up and down between the poles, the horns that is, when electric current is induced in the wire ring. As has been said, round the poles of the magnet there exists the state of electrical strain, a magnetic field. When the wire cuts this, electrons pass freely and with incredible rapidity from one atom of the copper wire to the next. Electricity is generated. The same thing would happen were the ring stationary and the magnetic field moved across it. The essential factor is the movement of the one thing relatively to the other. The direction in which the electric current flows depends on the direction in which the wire moves. During the upward movements, the current rushes one way through the circuit, in other words, the ring. During the downward movements, the current travels the opposite way. Such a current is therefore called alternating, since it takes either direction only during alternate movements of the conductor. This simple illustration explains the general principle, and it was from such a discovery, as we have said, that Faraday constructed the first dynamo for the generating of electricity. The generator. Briefly, a generator consists of a coil or coils of wire wound on a soft iron core to form a drum-like armature, as it is called. While the permanent magnet becomes an electromagnet, or a number of electromagnets, capable of creating very powerful magnetic fields. The armature is mounted on a shaft or spindle and revolved at high speed between the magnet poles, or it may be stationary, the magnets revolving around it. It should be noted that the armature coils do not represent our original wire ring completely, as they form only part of the circuit, the main part of which would consist of stationary wires leading the current wherever it is needed. If the armature itself revolves, it must be put in communication with the stationary part of the circuit by means of brushes, which are flat pieces of metal or blocks of carbon, which press upon smooth rings connected with the armature coils and revolving with them. Such a machine may be compared to a cylinder having its ends connected with the ends of a pipe. Just as a pump piston moving to and fro in a cylinder forces water to and fro through the pipe, so the generator drives electrical energy backwards and forwards through the conducting circuit, the reversal of direction occurring many times a second. We may say here that for some purposes, alternating current is not convenient. The term dynamo is commonly reserved for a class of generator which is so designed that it pumps current continuously in the same direction through the circuit. The current is then said to be continuous or direct. In dynamos, the armature is invariably the revolving part. The brushes which connect it with the circuit do not in this case press on separate rings, but on a single cylindrical drum, revolving with the armature and divided lengthwise into a number of insulated segments, each connected with some of the armature coils. The brushes make contact with it at points half a circle apart, so that if there be, say, 12 segments, they will be in contact with numbers 1 and 7, or with numbers 2 and 8, and so on, at any one moment. As it is impossible to go into further details here, it must suffice to say that the rotation of the commutator, as the divided cylinder is named, causes the pairs of segments successively to come against the brushes at the instant when otherwise reversal of flow would occur, and prevent reversal in the stationary part of the circuit by linking each brush with a coil in which current is traveling in the desired direction. To revert to this coil and permanent magnet illustration, the effect is equivalent to turning the coil over between movements, so that the same face of the coil cuts the field every time. Electric circuits. A current of electricity to maintain requires, of course, a complete circuit. That is to say, a current only flows between two poles, just as the current flows from the zinc element of an ordinary primary battery through a wire back to the carbon element. If the circuit be cut, the current stops. To take the case of a generator with an outside circuit, it delivers current to the circuit through one brush and receives it again through the other brush, that is, assuming the circuit to be complete. If there be a gap in it anywhere, if the circuit be open, the conditions necessary for electric induction are not fulfilled, and the armature will revolve easily and idly, generating no current but remaining in a state of excitation only. Directly the circuit is completed, however, current flows through it, its amount increasing or decreasing with the speed at which the dynamo is driven. If speed were allowed to increase indefinitely, the friction might ultimately cause the conductor to heat up to melting point. An ordinary circuit is normally in a broken or incomplete condition. The fixed conductors which form part of it are near each other, so that connection may be made between them where desired. On an electrified tramway, one conductor is represented by an overhead insulated wire, and the other by the rails which act as earth, and bonded conductors back to the source of supply. In itself, an insulated conductor carrying current is not dangerous. A bird may perch on it with immunity, and men who repair the overhead wires of tramways handle them safely with bare hands, because the platforms on which they work are insulated from the ground. But if a person touches both the insulated conductor and the earth or other conductor, he completes the circuit and may be killed at once. In continuous current circuits for traction purposes, it is usual to insulate the positive conductor and use the rails as the return or negative conductor. Generating power stations. Before considering how electrical energy is transmitted and distributed from the generating station to the points where it is required, let us see what goes on at one of the great electrical power stations. As a general rule, they do not convey to a visitor, who is no expert, any adequate impression of the scale on which such vast energy is being produced. There is no bustle and little visible movement, and not much from a spectacular point of view to excite one's wonder. The three principal power stations in London are at Chelsea, at Wood Lane, and at Neasden. From these power stations, the various underground railways receive the electrical energy which enables them to transport 571 million passengers a year. An enormous volume of fuel is required. One station alone consumes no less than 260,000 tons of coal per annum for the production of electric current. We shall see great steam turbines driving huge dynamos and alternators. At the Chelsea power station, the power is equal to 78,000 kilowatts, or about 100,000 horsepower. Current is supplied from these to 27 substations scattered about London. At these substations, the power is transformed into direct current to feed the live rails of various underground and electric railways and tramways. Distribution of current. Current is usually generated in its alternating form at a pressure of 3,000 volts upwards. A volt, it should be explained, is the electrical counterpart of the pound per square inch used to describe the pressure of gases or liquids. To one side of the powerhouse, perhaps in a separate chamber, will be found the switchboard on which are mounted electrical gauges for measuring the condition of current, and handles for operating the switches whereby current is controlled and directed. Where the generators are many in number, they may be divided into groups, each having its own switchboard. Just as the units of a battery of boilers contribute to their individual branch pipes and valves to a main steam pipe, so the generators of a group feed a set of short collecting conductors called bus bars through switches on the switchboard. By means of other switches, the bus bars can be linked with one or other of the sets of conductors which carry the current away from the powerhouse for distribution. And, where there are several groups of generators, provision is made for cross-connecting the several groups, enabling them to come to one another's aid when necessary. The switchboards collectively may be compared to the bridge of a ship. They are the center from which the brain and hand of the operators direct the mighty forces seeking an outlet. The movement of a lever may send current representing thousands of horsepower to a point within sight of the powerhouse, or start it on a journey of hundreds of miles. Current intended for local distribution may be turned into the mains straight from the generators, to be modified subsequently as will be described later. On the other hand, it may first be sent to transformers, by which its voltage or pressure is increased or stepped up, as electricians say. The loss in transmission due to the resistance of a conductor decreases rapidly with increase of pressure, or, to state the facts differently, the higher the pressure, the smaller may be the conductor for an equal loss. The cost of conductors is a very heavy item, so pressures have been raised again and again with increase in distance of transmission. 20 years ago, 50,000 volts was considered a very high pressure. Today lines are carrying current at 220,000 volts, and electricians look forward to much higher voltages still. After leaving the step-up transformers, the long-distance current flashes through insulated wires or cables, slung aloft on poles and trestles, and after a journey over maybe rivers, mountain passes and gorges, prairies and deserts, reaches the faraway station where it is to be distributed. Before admission to the switchboard, it has its pressure reduced by step-down transformers to a suitable level. The switchboard divides it among a number of different circuits. Some may be sent to substations, where it is converted into continuous current for operating tramways and suburban railways. Machines of the kind which effect this conversion may be heard buzzing in annexes to some of our tube stations. Other circuits supply power for running factories, and others again through small transformers dotted about over the area served. Energy for lighting and heating. At any of its many final destinations, the current may, of course, be passed through apparatus to suit it for any special purpose. The storage of electricity. The only method yet discovered of storing electrical energy in commercial quantities involves the use of accumulators or storage batteries, subdivided into a number of cells. In a cell are a number of plates or elements charged with chemicals and submerged in a liquid called electrolyte. The plates are interconnected to form two groups, those of one group alternating with those of the other group, and each group is connected with a terminal. If continuous current from an outside source be sent through the cell, certain interactions take place between the plate chemicals and the electrolyte, and electrical energy is converted into chemical. The cell thus becomes in effect a primary battery, willing to reconvert its chemical energy into electrical if the current be allowed to pass through a circuit in the reverse direction to that of its entry, and the chemicals to revert to their original condition. The amount of energy that can be stored in a cell depends on the size of the plates, and while the electrical pressure or voltage of a single cell is strictly limited, any pressure is obtainable by connecting together in series a sufficient number of cells. In the past, storage batteries as a class have suffered from several disadvantages, the most serious of which were their great weight relatively to capacity and the slow rate at which they could safely be charged and discharged. Recently, however, some important improvements have been made, which promise reductions of weight and charging time so great as to give an enormous impetus to the use of the independent accumulator and motor vehicle, which has some strong points in its favor, but has hitherto been restricted in radius of action speed. With the new batteries, a journey of 150 miles or more before recharging should be possible, and recharging be a matter of but a few minutes instead of hours. Even on the railway, the new accumulator may bring interesting developments. A 90-ton battery is estimated to have a capacity of 8,000 horsepower, equivalent to 1,000 horsepower exercised continuously for 8 hours. This energy would take a train from London to Edinburgh at express speed. Electric traction. An electric train or train hauled by an electric locomotive has a great advantage over the ordinary steam train, in that it gets into its stride much more quickly. A steam train starting from rest increases its speed by from 2/5 to half a mile per hour every second, whereas an electric train accelerates from a mile to a mile and a third per hour per second, and at the end of half a minute will be traveling at 30 to 40 miles per hour. This quick acceleration is exactly what is wanted in urban and suburban areas, where stops are frequent and traffic heavy, as it means a much higher average speed, shorter intervals between trains, and a great increase in the carrying capacity of a line. Actual figures show that scheduled speeds on lines converted from steam to electric traction have risen by 20 to 50%. During its operation by steam, the London District Railway carried a maximum of 18 trains per hour on the track, whereas the present electric trains run at intervals of about 1.5 minutes, or 42 in the hour at the busiest times of the day. The suburban electric train dispenses with a separate locomotive because the motors driving it are distributed among the coaches. There are usually 2 motors, each of 200 horsepower, under every other coach, so that a 6-car train has a propelling power totaling 1,200 horsepower. The distribution may be even more generous, but in any case the electric train is more highly powered than the steam train of equal length, and it must be so to negotiate at high speed the heavy gradients which engineers nowadays do not hesitate to include in an electrified track, though they would be rigorously excluded from a new steam-operated railway. The multiple unit system, as it is called, of train control enables any number of coaches to be coupled together without reducing speed capacity, as each unit contributes its proper proportion of power. At the same time, all the motors are as fully under the driver's control as they would be if concentrated in the locomotive. End of section 17. Recording by J.E.D. Klein, Ephrata, Washington.
Of the Outline of Science, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Noel O'Kelly. The Outline of Science by J. Arthur Thomson. Chapter 24. The Marvels of Electricity. Part 2. Powerful electric motors. A very large part of the electrical energy generated by the machines ultimately finds its way to electric motors, whereby it is reconverted into mechanical energy and made to do work. Thanks to the ease with which the electric motor can be connected to an electrical circuit, to its cleanliness, compactness, and generally accommodating nature, it finds countless uses, which are being added to every day. In size and power, the electric motor ranges from the tiny units attached to the dentist's drill, the desk fan or the carpet sweeper, to the great machines which drive rolling mills and propel huge ships. It has given navigators the revolutionary gyroscopic compass, which remains quite unaffected by the proximity of iron and steel. In mines it cuts, ventilates, drains, and hauls, penetrating whithersoever a man can go. Attached to pumps, it accompanies the diver into the holds of ships. During the war, the electrical submersible pump kept afloat many ships that without it would have foundered, and then, and since, has brought many sunken ships back to the surface. In the gold mines of the South African Rand, great economies have been effected by installing electrically driven turbine pumps at the bottom of the shafts to force water to the surface, in one case through a sheer half-mile. In California, electric motors developing 190,000 horsepower are used in agriculture alone, and the rice industry is almost entirely dependent on irrigation by electrically driven pumps. In many factories, complicated systems of belts and shafting have given way to motors connected directly to machine tools. The electric crane toys with loads up to 100 or more tons. The electric navvy scoops up several tons of earth or broken rocks at a bite 2 or 3 times a minute. Electric windlasses work the largest ships easily through the locks of the Panama Canal and haul boats, trains, and wagons up inclines. Electric traction, which has revolutionized transport in many respects and thereby affected our daily lives to no small extent, is based on the electric motor. In short, wherever motion is required, the electric motor is, if possible, pressed into service. Section 5. Big electrical feats. In Great Britain, the electrification of main railway lines is in its infancy. On the continent and in the United States it has been developed considerably. Switzerland, Austria, and Italy are electrifying long stretches of their railways, and tunnel sections through the Alps have been worked by electric locomotives for some time past. The longest all-electric runs are in the United States, and electrification is revolutionizing heavy haulage. trains of 5,000 tons are handled in easier sections, and even heavier combinations are foreshadowed. Naturally, America has most to show in the way of mammoth electric locomotives and the biggest electrical engineering feats. Here, physical and other conditions demand engines of great power. We have heard a great deal about the mighty steam mallet locomotives, some of them weighing over 400 tons, but not so much about their electric rivals. Some time ago, a unique contest between steam and electricity was carried out at Erie. Two powerful modern steam engines of the class used for hauling the big limited trains on the New York Central Railway were linked together and pitted in a pushing match against a single electric locomotive, designed for similar service on the most westerly section of the Chicago, Milwaukee, and St. Paul Railway. The electric pusher was driven backward some distance without opposition, but when current was switched into its motors, the steam engines were gradually brought to a stop and then made to retreat in a regular route with throttle still full open. Surely an omen of the future. The tests included another of great interest. The electric locomotive was driven ahead for a time by the others, then it was called upon to check them, which it did by simply reversing the motors so that they acted like dynamos and pumped power into the conductors and back to the power station, the contribution amounting at times to over 2,600 horsepower. In America, great stretches of main lines have been electrified and are worked by electric passenger and freight locomotives of up to 4,000 horsepower. The feats performed by some of these monsters in mountainous districts are indeed astonishing. On the Norfolk and Western Railway, coal trains of 3,250 tons are taken up 2% grades by two electric haulers at double the speed previously attained by three of the largest mallet steam locomotives. This is but one instance out of many that could be quoted. The secret of the electric locomotive's colossal strength is, of course, that a very much larger percentage of its total weight can be devoted to the apparatus that gives rotations to its wheels, since it draws its energy from an outside source instead of from a ponderous boiler. Climbing the Rocky Mountains. The longest stretches of main line yet electrified are on the Chicago, Milwaukee, and St. Paul Railway, the most recently completed of the transcontinentals. One of these, the Rocky Mountains section, is 440 miles long, and the other, the Cascade Mountains section from Othello to Tacoma, 211 miles long. The gap of 200 miles on the flatter country between them will in due course be electrified also, and a continuous run of over 800 miles by electric power be possible. These sections include many long and severe grades, sharp curves, and many tunnels, and generally taxed steam traction to the utmost, especially in winter when the steam trains were liable to get frozen up during enforced halts. Running times have been cut down by 1/3 since electrification. The sections are supplied by several power houses with current transmitted as alternating current at 100,000 to 110,000 volts to substations distributed at intervals of about 30 miles along the line, where it is stepped down and converted into 3,000-volt direct current for feeding to the overhead conductors. The same general principles are adopted for most electrified railways, though the pressures and distances may be different. It is interesting to note here that the power needed to pull trains up the slopes of mountains in some places is now largely supplied by the weight of water falling down in other places. what may be called a balanced lift effect is produced through the medium of the water turbine and the powerhouse. Swiss waterfalls, in this roundabout fashion, move trains through summit tunnels and carry them up high peaks, even to within a few hundred feet of the Jungfrau's crest. By a lavish snow or rainfall at high elevations, nature atones in many countries for the absence of fuel. Now that man knows how to use it, white coal is able to replace black. People whose experience of electrified lines is limited to suburban tracks may regard electric haulage as slower than steam. It may therefore be pointed out that the highest speed ever attained on a railway, 131 miles per hour, was made by an electric locomotive as long ago as 1903. The conditions certainly were abnormal, as a special track had been prepared. So, to set any doubts at rest, it should be added that, where main lines are operated electrically, express speeds are around 60 miles an hour, or as high as are permissible on an ordinary track worked under economical conditions. Where coal has to be used as the source of power, there is no question about the economy in fuel given by electrification. The amount saved in a year by the transcontinental railway referred to, on its electrified sections, would, according to an authoritative statement, suffice to move 270 ocean liners, each of 13,000 tons displacement, from the United States to France and back again. Section 6. Electricity from waterfalls. The utilization of water power on a large scale in the production of electrical power is made possible by the dynamo and the electric motor. We have only to go to the famous Niagara Falls to witness the conversion on a large scale of the energy of falling water into electrical power. There, within a space of a few square miles, are to be found more generating stations operated by water than in any other equal area of the Earth's surface. The conditions are ideal. The Niagara River, connecting Lake Erie with Lake Ontario, falls through a vertical distance of over 330 feet during a few miles of its course, including the sheer drop of 159 feet of the falls proper. Every second, more than 220,000 cubic feet of water plunge over the rocky ledge into the whirlpool beneath. A simple mathematical calculation will show that the potential energy of this fall and flow combined represents about 8 million horsepower. During the last 20 years, several generating stations have risen successfully beside the Niagara River, some of them above and others below the falls. Sufficient water is now deflected from the last, without injury to their beauty, to supply the neighborhood and towns within a radius of 100 miles with a bountiful and cheap supply of electric current. Already the falls of Niagara alone furnish 500,000 horsepower for lighting and traction to Canadian and American cities. When the full program is completed, the amount will be doubled. The visitor unversed in engineering science might expect to find at Niagara enlarged editions of the water wheels which are picturesque features of many of our streams. As a matter of fact, there is not such a wheel to be seen. The water motors used, turbines, are hidden away under the roofs of the power houses. Each of the 8 plants has its distinctive characteristics, but they all depend on certain principles. Drawing power from an upper level, leading it down to a lower level through great steel tubes called penstocks, passing it through turbines, and finally discharging it into the river below the falls at a velocity much less than it would acquire in a straight drop through the same distance. In order to get a sufficient fall, the Niagara Falls schemes included the sinking through the rock of great vertical rectangular pits, 150 or more feet deep, at the bottom of which turbines are located, and the driving of long tunnels to carry the water away from the pits after it has done its work in the turbines. The penstocks feeding the latter are attached to the sides of the pits, and the turbines are connected by long shafts with the rotating parts of their respective generators in the powerhouse far above. Great engineering feats. It is impossible to even mention here the many great engineering feats performed at Niagara in connection with the various power schemes, but passing reference may be made to two notable discharge tunnels driven 7,000 and 2,000 feet respectively through the rock. The former is reputed to be one of the largest tunnels in the world as regards size of section, and it is otherwise interesting as having its exit behind the water curtain of the Canadian Falls. Taking schemes separately, the latest is undoubtedly the most imposing, as it makes use of a total fall of over 300 feet, or about twice that utilized by most of the earlier installation. The falls are, in this case, turned by a canal 12.5 miles in length, which draws water from the Welland River, entering the Niagara River a long way above the falls, and leads it to near Queenston, below the lower rapids, where a huge powerhouse is being erected at the water's edge. This will ultimately contain 10 units of 40,000 electrical horsepower each. The construction of the canal required the excavation of over 13 million cubic yards of material, mostly rock. And so great is the flow through the new channel that the current in the Welland River has been reversed between the junction with the Niagara River and the entrance to the canal. How water turbines work. We can give here only a brief description of the water turbines used at Niagara. The type mounted at the bottom of the deep pits there, referred to in an earlier paragraph, has a large upright barrel-like fixed chamber into which the penstock, the steel tubes, delivers the water under high pressure, and a vertical shaft passing through the ends of the barrel, with two large discs attached to it of larger diameter than the barrel. The discs are outside and almost touching the ends, and round their circumference are attached upright rings of vanes which overlap the barrel, so as to be opposite rings of guide blades fixed in openings near the barrel's ends. The water gushing outwards through the guides strikes the wheel vanes at an effective angle and drives the discs round and round, and the shaft with them. Outside the moving vanes are solid rings which can be raised or lowered by an automatic governor to regulate the rate of escape of the water and the speed at which the turbine runs. The turbines in the powerhouses below the falls are differently arranged. They stand beside the generators on the same floor, and their shafts are horizontal and short. The water enters a ring-shaped chamber, open on its inner side, and passes through the guides on the blades of an internal wheel, which alters the flow of the water and discharges it in a direction parallel to the shaft. Few of the Niagara turbines are of less than 5,000 horsepower. Many develop 10,000 horsepower, and some of the latest 45,000 horsepower. Some of the generators which they drive are the largest yet built, weighing 300 to 400 tons apiece. The Pelton Wheel, though not employed in the Niagara plants, is widely used in power stations for coupling to generators where water is available at very high pressures. A wheel consists of a large disc with pairs of cups distributed around its circumference. A jet of water issuing at high velocity from a nozzle strikes the knife-like division between a pair of cups and is split right and left into two streams which pass around the inside of the cups, and by reversing their direction in doing so impart all their energy to the cups, which travel forward at half the speed of the jet. The most remarkable Pelton Wheel plant is probably that at Fully, Switzerland. Water is here led downwards from a lake through a pipe 3 miles long, which in its short course sinks more than a mile, say through 6 times the height of the Eiffel Tower, so that at the lower end the pressure in the pipe exceeds a ton per square inch. The water leaves the nozzle at a speed of nearly 400 miles per hour, and, though the wheels are 12 feet in diameter, revolves them 500 times per minute. It may be mentioned in passing that the resistance offered by rapidly moving water to any attempt to deflect its course is remarkable. A jet 3 inches in diameter, emerging under a pressure of 500 pounds per square inch, cannot be cut through by a blow with a crowbar. Steam turbines. In steam-operated power stations, where the larger part of the electrical energy used by man is still generated, the steam turbine coupled direct to a generator is the counterpart of the water turbine. A steam turbine of the Parsons type consists of a long closed horizontal drum mounted on a shaft in a strong casing, through the ends of which the shaft passes. The annular clearance space between the drum and casing increases by stages, as the latter is stepped, and this space is filled by rows of curved blades, alternate rows being attached to the drum and those between them to the casing. The tips of the drum blades just do not touch the casing, while those on the casing just clear the drum and the other blades. In a large turbine there may be some hundreds of thousands of blades, of lengths ranging from an inch to over a foot. Steam is admitted at the smaller end of the casing and threads its way through the many rows of guide and moving blades, each one of the last getting a sideways push which is transmitted through drum and shaft to the generator. After expanding greatly, the steam escapes to the condenser, either direct or after doing further duty in another turbine. A turbine is so well balanced and revolves 1,000 times or more per minute so smoothly that a coin stud on edge on the casing is not upset. Section 7. Importance of water power. The scale on which the world's water powers have been explored and developed during the last 10 years is one of the most significant engineering features of the decade. 3 times as much water power is used now as was used 10 years ago. The advance has naturally been most rapid in those countries which have depended in the past for their power largely on imported fuel, where white coal may be substituted for black. Thus, France has added 850,000 horsepower to the 750,000 horsepower of 1915. Switzerland now has some 1.5 million horsepower as compared with 850,000 horsepower in 1914. The output in Spain is 900,000 horsepower as against 150,000 horsepower before the war, and that country is engaged on a scheme for developing a further 2 million horsepower. The same kind of story may be told of Canada, the United States, Italy, Japan, Norway, Sweden, and India, where also the water turbine is rapidly altering industrial conditions, despite the liberal coal deposits in some of those countries. The world's total potential water power has been calculated at 200 million horsepower. Estimates must be accepted with reserve, as the surveys, which have necessarily been very incomplete in the almost unexplored regions where ultimately some of the greatest developments may be expected. So far, only 25 million horsepower of this energy has been turned to account. Even at this stage, however, the economies resulting from harnessing water power are apparent. In the best steam plant of large size, 9 tons of coal must be burned to give 1 horsepower continuously for a year. Therefore, 225 million tons of coal, or approximately the whole output of our coal mines per annum, represent the amount that would have to be fed to boilers to produce the energy of water already doing service. The world's total water power would, on this basis, exceed that obtainable from the world's coal output in 1913. It may be that the development of water power will, in the future, affect the center of gravity of the world's industries, for these tend to move towards cheap power. A rather interesting illustration presents itself. In North Sweden are vast deposits of iron ore, formerly mined for smelting in England and other coal-producing countries. But Sweden, though poor in native coal, is rich in water power, now being developed to run great electric furnaces in which the ore will be converted into iron and steel, thus enabling her to compete in the world's markets under favorable conditions. Her waterfalls have given Norway a new industrial importance. Who shall say that a country like Brazil, with its estimated 26 million horsepower, and British Guiana, the Zambezi Basin, New Zealand, and other naturally favored countries may not, in future years, become industrially important, thanks to the energy of falling water? Section 8. Electric lighting. It is unnecessary to discuss what we owe to electricity in the form of light. It is evident to everyone. If an electric current be forced through a very fine wire, able to stand extremely high temperatures without melting, the resistance encountered causes the generation of heat, which is partly converted into that form of energy called light. In this way we get the incandescent electric lamp, which is simply a fine wire of tungsten enclosed in a glass bulb, from which all the air is exhausted to prevent the metal being burnt by a combination with oxygen, the wire being made white-hot by the current. We may admit, after exhaustion, a little inert gas, which has no effect on the filament. The lamp is then known as gas-filled. Adding the gas makes the lamp more economical, since it gives considerably more light per unit of current consumed, and this is why the gas-filled lamp, made in strengths up to several thousand candle power, has largely replaced the arc lamp. In an arc lamp, 2 carbon pencils connected with the circuit are brought together point to point. The tips become white-hot, and if they now be separated slightly, atoms of incandescent carbon leap across the gap from one tip to the other in a continuous and intensely luminous stream, which is called an arc, because the path of its particles is curved. An arc lamp includes apparatus which automatically keeps the pencils the correct distance apart as they burn away, allows them to fall together when the current is switched off, and draws them apart to start the arc when current is switched on. Though more troublesome than the incandescent filament lamp, the arc can be much more powerful, and, as its light proceeds from a very small area, the rays may be accurately focused by lenses and mirrors and projected in an intensely luminous beam, such as is required for searchlights and cinema projectors. Arc lights of up to 90 million candle power are used in lighthouses. There was, and perhaps still is, at a station on the Jungfrau Railway, a lamp that projected a beam visible for 60 miles, which enabled a newspaper to be read in the streets of Thun, 35 miles away. Though, where current is cheap, electric is the cheapest possible form of artificial lighting, besides being far the most convenient, from a scientific point of view it leaves much to be desired. About 19/20ths of the current that produces it, is dissipated as heat, and where it depends ultimately on coal, only about 1 part in 100 of the coal's energy is converted into light. It has been said that if we could convert energy into light as economically as the glowworm, a single boy turning a handle could light a fair-sized town. There are evidently great fields still to conquer in the realm of electric illumination. Electric heating. For heating purposes, electricity is much more efficient, since electrical energy is only too willing to change into heat. One of the difficulties associated with large electrical apparatus is that of keeping parts cool enough to prevent insulation being burnt away. Domestic electrical heating appliances derive their heat from wires or very thin films of metal or other suitable material through which current is passed in sufficient strength to make them glow. Some electric radiators are practically the same as incandescent lamps in design and construction. Others, again, are mere wires wound on refractory material and exposed to the air. Electric irons, hot plates, kettles, etc., have the conductor embedded in mica or asbestos in close contact to a metal cover through which the heat is conducted to the matter to be heated. There are very few cooking or heating operations that cannot be performed electrically, so that we now have, besides electric ovens and hot plates, electrically heated soldering apparatus, glue pots, foot warmers, cigar lighters, bed quilts, and so on. The aeroplane pilot, soaring many thousands of feet above the earth, would often be paralyzed by the intense cold but for the meshwork of insulated wires hidden in his gloves and other clothing, which distributes a grateful warmth due, when traced back to its source, to a small propeller driving a dynamo. Only a comparatively small part of the electrical energy that is purposely converted into heat is used for domestic purposes, however. Vast quantities of electrical power are now generated for heating furnaces in which are produced all the aluminium we use, all the calcium carbide from which acetylene gas is made, all artificial abrasives, and certain fertilizers containing nitrogen stolen from the atmosphere. Electrical furnaces now smelt iron and convert it into high-quality steels by the 100,000 tons. The furnaces are in principle enlarged editions of the arc lamp and domestic resistance heater, and all taken together they consume millions of electrical horsepower continuously. A very important branch of electric heating is that concerned with welding. The electric current has given the engineer an invaluable ally when dealing with repairs to heavy machinery. A typical instance of its helpfulness is supplied by what happened during the war, when enemy vessels interned in American ports had their boilers and engines rendered useless before abandonment. Under old conditions, the only remedy would have been to replace the injured parts by new ones. But with the aid of the electric arc it was possible to unite the edges of broken pieces and affix patches so securely as to render broken machinery as good as new in effectiveness, if not in appearance. The result was that in a very short time many large ships that the enemy regarded as definitely hors de combat were ploughing the seas again and doing useful service. The electric weld is replacing the rivet in many manufacturing processes. The steel plates of a ship's skin may now be joined together without the use of a single rivet, and welded vessels are actually in commission. Many articles of everyday use are electrically welded. To make a spot or local weld, the parts to be joined are pressed together between the points of bars connected with an electric circuit, and the heat set up by the current causes the parts to fuse and amalgamate over an area between the bars. Again, suppose a short bar has to be affixed to a thick plate to project from it. Instead of drilling a hole in the plate, tapping a thread in it and cutting a thread on the bar, the last is merely pressed against the plate and a powerful current passed through both parts, and in a few minutes the two are practically one. End of Chapter 18. Recording by Noel O'Kelly.